and it lets us run theatrical smoke into the diffusers and show the air pattern once the air enters the room. This is a unique opportunity because most in real life you don't get to see air, and of course you definitely would not want smoke like this flowing through the room. So this allows us to visualize that air movement in a safe and consistent way. Most of the systems we'll be showing in this presentation are mixed air systems, as that is by far the most common form of air distribution in commercial buildings. We'll show multiple different products and how they produce these high velocity jets. A mixed air system is primarily defined by its ability to use high velocity air jets across the ceiling to ensure that there's uniform air temperature and air quality throughout the space. It's important that we move the air this long of a distance because that ensures that all of that fresh, filtered, and outdoor air that we are conditioning is able to reach every occupant. Most typically in cooling applications and in general, most applications, we would supply air with cool air, usually somewhere around 55 degrees. And then if we are doing some type of heating mode, we would want to heat up the air to closer to maybe 85 degrees. Doesn't always have to be these temperatures exactly, but these are typical rules of thumb. We would not want our warm air to be much warmer than that. As our supplier gets warmer and warmer, it becomes more buoyant and will actually want to hug the ceiling and not come down to the floor. In fact, ASHRAE gives us penalties to our ventilation rate if our supplier temperature is too warm. This would assume that there would be some fraction of that overheated air that can't reach the floor. Oftentimes we actually control the room temperature, not necessarily by adjusting the supplier temperature, but just by adjusting the supplier volume. As we can assess, in order to achieve a room temperature, there needs to be some type of steady state condition where the cooling that we are providing for a room matches with the heat loads that are already existing in the room. A very practical way to adjust how much we're cooling the space is to simply put a damper within a ductwork and have that adjust accordingly to either provide more airflow or less airflow, and thus more cooling or less cooling. Oftentimes the thermostat on our wall, if it's calling for a different temperature than what the room actually is, it'll send a signal to a damper upstream to adjust the airflow until we hit that steady state condition. When this happens, we call this a VAV system. So here's a full example of what that mixed air system looks like. When the airflow starts, it leaves the diffuser at a high velocity. This might be anywhere between maybe 500 up to 1,000 feet per minute neck velocity. Any higher than that, and we start generating too much noise. And the air will discharge, usually in a horizontal plane, across the ceiling, and it'll make its way to the walls. The air will then continue down adjacent walls until it enters the occupied zone. We generally define the occupied zone as 6 feet above the floor. And by the time the air reaches 6 feet above the floor, we would want it to have slowed down to about 50 feet per minute. This is a rule of thumb velocity from which we would or would not perceive a draft. Also, by the time the air has slowed down to 50 feet per minute, it has also induced enough of the rest of the room air that it's actually warmed up such that we're no longer at 55 degrees Fahrenheit. That air jet has actually warmed up to room temperature. The air then continues down the wall and mixes within the occupied zone. As we see just from this single diffuser, we have equal air distribution throughout the entire space, which is good because that ensures that there is no stagnant zone in the corners of the room. that our temperature is uniform, our contaminant concentration is uniform as well. It also makes sure that any contaminants that were present in any corners of the room become diluted throughout the space. Finally, that mixed room air will actually be induced back up to the ceiling, and we can actually very clearly see this induction action. It loops upwards and continues the cycle. The reason for this is because that high velocity air jet has uh, high velocity pressure but low static pressure. So it actually acts almost like a vacuum up at the ceiling that causes the rest of the room air to move upwards. This continues perpetually until uh, we, well, it continues perpetually to condition the space. There are times where it's good to push our air jets onto warm or cold surfaces, most specifically exterior walls. If we have a worst case summer day or a worst case winter day, our exterior walls are major heat sources for the space. Either we're going to dissipate heat to the outdoors, or that wall surface is going to be warm and we're going to bring heat inwards. Uh, us supplying air directly onto that surface helps mitigate that surface temperature and eliminates any radiant component of that heat transfer to the occupants. It also, very importantly, warms up any cold surfaces that might otherwise be below dew point. So uh, this would prevent any condensation buildup on those cold exterior walls. We want to be careful about any other obstructions within the ceiling plane itself. We certainly share the ceiling with other trades, whether it's lighting or fire sprinklers or any architectural elements. And if we may have a perfectly engineered air distribution system, perfectly sized diffuser, perfectly sized fan, just the right airflow. But if we have an obstruction in the ceiling that collides with that air jet, it can cause our airflow to drop straight downwards and create a draft on an occupant. Um, the best ways to avoid this is certainly if we have the option to adjust the position of the diffuser, but otherwise we always want to be cognizant and try to collaborate with the other trades to prevent this from happening. As a rule of thumb, we would say that if the obstruction creates a 10-degree angle or greater between itself and the diffuser, then it is a large enough obstruction to create this drop of the air jet. But if the obstruction is smaller, say it has less than the 10-degree angle between itself and the diffuser, then it's small enough that the air jet will likely just curl around it. 10 degrees is just a basic rule of thumb. It's the actual physics is more complicated if you look into it, but might be 15 degrees, might even be 20 degrees. But we like to say 10 just to be conservative. Sometimes occupants like to have their own personal fans in their space, and this actually, for a mixed air system, does not significantly affect the room air motion. In this video, we actually have a box fan blowing upwards towards the diffuser, and as we see, the diffuser is still mixing throughout the space. Uh, we get a little bit of traction with that fan airflow, but the reality is a mixed system is a mixed system. If you introduce a fan, it just makes it more of a mixed system. Really all an in-room fan would do is, for the most part, increase the local velocity at the occupant and maybe cool them down more. But we're not at a concern of ruining the performance of the diffuser itself. Now we're going to change gears and look at stratified systems. So you can tell that this is a fundamentally different form of air distribution. There's no high velocity. The air is being supplied at actually a face velocity of 40 feet per minute from this grill. The air drops down to the floor because it's slightly cooler than the rest of the room, usually somewhere between 62 and 68 degrees Fahrenheit, and that'll continue to blanket the floor, almost like you're taking a bucket of water and pouring it across the ground. Now, when that cool, fresh air finds a heat source, such as our thermal mannequins here, the heat from the sources themselves causes the air around it to warm up and become more buoyant and rise up to the ceiling. These thermal mannequins simulate the same heat load as human occupants, and so we actually would see this same thermal plume effect from humans. The benefit of this is that occupants are often the sources of contaminants for a room themselves, whether it's from breathing or skin particles or any other airborne particles that they create. And in this system, those contaminants will then be warmer and essentially move straight up to the ceiling and out the return instead of mixing throughout the entire room. This gives a stratified system better ventilation effectiveness and ultimately fresher air to the occupants. Here's an example of it filling an entire room. What's interesting about a stratified system is that there is no forced air, there is no initial air velocity, and thus we're not that concerned about the initial position of the diffuser. It can be in one corner, it can be in the wall, it can come from the floor. There are some overhead versions of displacement as well. Either way, the air will find its way to the heat loads because the heat loads are what drives the room air motion. Even if these mannequins were all the way to the left side of the screen, we would see that supply air follow the mannequins because they are what demand the airflow itself. Which is exactly what we see in this video, um, the heat moving over to the corner, or sorry, the airflow moving over to the corner. There's a general maximum distance rule of thumb that we would say of about 30 feet distance from a grill. If we have a room larger than that, then we would simply want to add more displacement grills to the opposite corner. Every so often, someone wants to maybe introduce a fan, an internal fan to a stratified system because they want to maybe ventilate it better, quote unquote. But that is strongly not recommended for as we introduce any high velocity air current to a stratified system, that causes all that air to essentially become a mixed system again, and it removes our stratification. If we are doing stratified, we want to be cognizant of any sources of high velocity currents and from a design perspective, not design them into the room. However, if someone is just walking through a room, the actual typical walking speed of occupants can be anywhere between 100 and even 300 feet per minute if they're walking quickly, which, as you may recognize, is far higher than our design flow rate for overhead mixing or stratified systems within the occupied zone. This is not inherently bad for when someone is actually walking. That means they are on a focused task and they're less concerned about drafts and currents in their movement. Uh, the movement of occupants themselves do create a little bit of an air current behind them, as we can see in the video, but it's not so bad that it disrupts a stratified system in any significant way. In summary, mixed air systems function primarily by supplying air at high velocities. They intentionally create room air motion throughout the space continuously, which creates a uniform temperature and air quality throughout the entire zone. Our main design parameter is to maintain air velocity of at least less than 50 feet per minute within the occupied zone itself. We also recommend pushing air jets onto any surfaces that are expected to be very cold or very warm, such as an exterior wall or window, in order to regulate the surface temperature, mitigate thermal radiant effects, and eliminate a risk of condensation. And then finally, stratified systems such as displacement ventilation function very differently. They rely on the heat loads within the space themselves to drive the air upwards, resulting in higher ventilation effectiveness. For more information, I will refer you to the Price Engineering Handbook, Chapter 9, as well as various ASHRAE standards and references for the design of these systems. You may also reach out to our GRD and Stratify teams at Price Industries to answer any specific application questions you may have. That concludes this presentation, and thank you for watching.